normalize his internal pressure, so I just use it. It is also convenient. It reduces the equations nice. Okay, other possibility is, let us say you have external pressure as your eigenvalue, right? We know that shells under external pressure can also buckle. This is actually particular for the situation of hydrostatic pressure. Hydrostatic pressure is that you not only have lateral pressure, you have also pressure on the top and the bottom of the shell. That means that lambda, the normalized axial load, is in a constant ratio with the lateral pressure. That constant ratio is this r cap. I shall show it on the next slide. You can write the eigenvalue in this very simple form. Once again, the next slide shows the normalizations. We have seen this, this, and that. We have seen lambda. P sub E is the same as before. Here is something new, r cap, the ratio between the end load, lambda, and the lateral load. And if you have hydrostatic pressure, the value of this ratio is precisely 1/2. Any other ratio you can also fix, but I mean that would be very artificial. I can think only of one situation where this is very useful, is that you have this shell, let us say, sitting in a tank, and you keep, by pumping additional pressure into the tank, you increase the pressure both laterally and on the tops, and then the ratio is precisely 1/2. Okay. Now, the B factor, what is it like? For orthotropic shells, this has been derived by Hutchinson and Amazigo in 1967, and essentially it can be written in such an infinite series. You sum over odd terms only. I have not written down what these terms are. I mean, there are long expressions involving, once again, wall stiffness and wave number parameters. The important thing is that this here goes like 1 over j, and this goes j over j squared minus 4m squared, and it converges rather fast. You can do it on the computer. You can say, take 200 terms, for instance, as an upper limit, or whenever the change, the additional term, is less than the 5th digit, and you stop with it. Notice once again, there is a limitation, right? Because you cannot have here, why can you not have even numbers for j? Because then this thing would blow up. So must remember the summation goes only over odd integers. All right, now, essentially now, I would have to have, this is from a lecture that I gave in Lyon, and there we had a Sun workstation sitting next to me, and essentially there are ways of hooking what you see on the screen to a projector and project it next to it. So essentially, there we demonstrated that you can, takes about 5-6 seconds to calculate one of these curves with our software, and essentially you had then 2 pictures. You could see that comes out of their publication, and here was what we calculated. But now it is interesting to see what type of information they generated. I think these are type of information that are very helpful for shell designers. Why is that so? He says, I have here a certain combination of stiffener parameters. This is for axially compressed stringer stiffened shell. What are the parameters? A sub s is the area of the stringer. D sub s is the distance between successive stringers. T is the wall thickness of the shell. So he said this is lightly stiffened. Its value is 0.5. Then here you have a parameter that tells you what is the bending stiffness of the stringer, because I sub s is its moment of inertia with respect to the CG of the stiffener. E is Young's modulus. D is the bending stiffness. E, T cubed divided by 12, 1 minus nu squared of the wall. And ds is once again a parameter that gives you the spacing of the stringers. And that he chosen as 20. Then you can put the stringers on the outside or on the inside. And that is this ratio eccentricity, that is the distance between the center of gravity of the stringer area and the mid-surface of the shell, divided by the wall thickness. If it is 3, it is on the outside. If it is -3, it is on the inside. It's a well-known fact that if you put the stringers on the inside, the shell will carry less. And here you have once again Bottorff's Z parameter. You can think of this as follows. If you make a shell of a certain radius thickness and of a certain material, then, and that is given, then a small Z means that it is short, because on the top it is L squared, and a big Z means that the shell is long. Okay? So let us say we think of it short this way, long that way. And essentially, here you have the normalized buckling load, and it says that as you make your shells shorter, they can carry more load. And outside and inside stiffeners, the outside stiffeners are stronger than the inside. And here is a curve. If you have the stringer placed in such a way on the shell wall that the CG of the stiffener coincides with the mid-surface, symmetrically spaced. Okay, and B factor, you notice that for outside you get once again this big decrease here for short, which has been tackled and essentially found that if you do a rigorous analysis it might disappear. This is when the stringer is symmetrically spaced, and notice that if it is inside it is not very much sensitive to initial imperfections. Here is another one. The only difference is for medium stiffeners, and then that all comes out of their paper. And here is one for heavy stiffeners. Okay? Now, the big selling point, I think, of this deco of capabilities is that if you are an engineer, you know of this theory, you want to use it. If you don't have this deco, all you have those plots. Now let us suppose your stiffener parameters don't precisely match those that have been published. What possibilities you have? You may try to interpolate. Huh? How accurate it is, nobody knows. If you have this deco, never mind. This deco accepts input. You put in your stiffener parameters, and for your particular shell, within 5 to 10 seconds, you have the value. So you don't have to interpolate. You can use it. Okay, this is another one. From the same shell, axially compressed, the effect of axisymmetric imperfections. It is rather heavily stiffened, as you see, and it shows that for different Z, and this is a rather short shell, if you have an axisymmetric imperfection, which is a half-wave sign, you get a rather pronounced decrease. Note as well that it is not 1 there, that's 4. So that if you take 1, as I've shown the most other pictures, then the effect of imperfections is not so strong. Okay? So to get a decrease of 60% for a Z of 60, you will have to have an imperfection which is 4 times the wall thickness. And that's rather big. Another one. This is then for external pressure. Once again, you have light, medium, heavy. There are the parameters. Once again, here you have the buckling loads, the stiffeners on the outside or on the inside. And here you have the corresponding B factors. Notice that if you start stiffening the shells, the decrease is considerably their imperfection sensitivity, because the curve for the unstiffened, also for the externally pressurized isotropic shell, has a considerably lower buckling load, right? And is also imperfection sensitive. So here, if you are a design engineer and you have a choice, you would, I suppose, go with ring stiffened shells. Now, the same thing here for the stringer stiffened shell. I kind of just browse through those, because without really showing the other thing next to it, they are not that interesting. This here is externally ring-stiffened shell under axial compression, the effect of axisymmetric imperfections. And once again, you see that you have different